So, thanks to everybody for coming. This is our June meeting of New Mexicans for Science and Reason. And tonight's topic is revisiting earthquake lights. And we have an interesting video that a YouTuber, Anton, has posted. It's about a 13-minute video that really has an interesting update on the whole earthquake lights phenomena. And then we've got just an awesome panel. So we've got Alberto Enriquez in the house. And are you still a journalist? What are you up to right now? Oh, can't hear you. Oh,
I'm retired now, and I'm living in Medford, Oregon, gardening.
Okay, well, that sounds admirable. And we've also got John Derr, geophysicist and earthquake expert, now retired from USGS. And we've got Friedemann Freund, who I looked up is a senior research scientist with the SETI Institute. Is that what you're still doing?
Yes, I'm still doing it, and I'm also affiliated with the NASA Ames Research Center.
NASA Ames, great. So, anybody want to just have some introductory comments before we launch into this video?
No,
I'll go ahead and say that I'm really pleased to be here with Friedemann Freund and John Derr, who are two of the most seminal figures in earthquake forecasting and anything to do with pre-earthquake. John is quite simply the bravest USGS employee who ever lived. He came out for pre-earthquake back in the 60s or 70s. I don't remember that far back, but he stuck to his guns, and that doesn't help anybody's career at USGS, as it turns out. And they have steadily tried to stymie and block progress in this field, and they have failed miserably. I mean, this is an agency that was slow to adopt INSAR or to involve itself in the development of INSAR or GPS. You would think those would be right up its alley. They didn't do it. NASA and the Defense Department did, and that was very slow to adopt for decades continental drift theory, which later was trotted out as tectonic theory. But certainly Alfred Wegener had 7 independent lines of evidence showing that continents did move. And you don't get any better than that in science than to have 7 independent lines of evidence. So, but he was dead for 30 years before America was willing to admit that it was a fact. And Friedemann Freund is the innovator, genius behind positive hole theory, which explains all of the earthquake precursors. And he had to do that virtually single-handedly. Much of the funding came from his wife's work as a award-winning novelist in Germany and Japan, because again, all research grants through USGS were blocked. Thank God that he kept going and is still going, and that we still have him with us. Not only is Freund an expert in pre-earthquake, but he's also an expert in abiogenesis, the origins of life, because his theories also touch on synthesis of organic compounds in interstellar grains. I can even pronounce all the stuff that these people do. Oh, and there we see his wife, Hisako Matsubara, the award-winning novelist herself. We love you. Thank you for supporting the work.
Okay. I just came back from the office, so Hisako wanted to say hello. So Yes, I'm very happy to join this team, and I'm eager to learn what you have been discussing in the past, and I'm ready to answer any questions. And I'm particularly, of course, happy to see Alberto again and to see John Derr. So John Derr, I think we have been in touch for more than 20 years, and I don't remember whether we actually ever met in person, but
No,
your name is
we never have.
yes, we never have, but your name is linked with all the things that I have been interested in, namely in connection with earthquake in the very broad sense. And
Thank you, Friedemann. You tie it all together.
thank you so much for saying so. Well, yeah, that's my introduction.
Excellent. Thanks. John, did you have anything to contribute before we get in the video?
I'll just thank Alberto for his very fine summary. He is one of the most verbal people in the field, writes extensively and very well. I first heard about Alberto when he was writing for the Anchorage Daily News many years ago, and we have been in touch by email, mostly occasionally by phone ever since. So there's not much I can add to what's been said already. I'm probably just wasting time if I continue talking. So I'll let you go ahead.
Okay, that was a great introduction. So we do have a resource on nmsr.org, and that is a write-up of the presentation Alberto gave back in 2008. And so that links to this YouTube video, a new YouTube video from last May by Anton Petrov, who has a pretty popular channel. He usually talks about black holes, new galaxy discoveries, just general, what's new in science and physics. Pretty fun, informative channel. But he's picked up on earthquake lights and some new research, so let's switch over to that. I'm gonna make sure we got sound, and we'll just go to go.
Yes.
Back in 1988, somewhere in the province of Quebec in Canada, there was an unusual pink-purple globe detected flying above the St. Lawrence River. An object whose nature and whose origins were unknown for many years, technically still unknown today. And although initially it was obviously assumed to be some kind of a UFO or potentially some other mysterious and hard to explain phenomenon, eventually it was followed by something else. It was followed by an earthquake. And this is where our story begins. Hello wonderful person, this is Anton, and today I wanted to talk about this really interesting concept that's technically becoming an actual scientific concept simply because of the amount of evidence that seems to suggest it actually exists. And no, we're not talking about UFOs, mostly because I still think it's nothing to do with science. We're talking about something way more interesting in my opinion. We're talking about earthquake lights. These strange phenomena that seem to appear during very powerful earthquakes and that in theory could actually explain various UFO phenomena as well. And one of the main reasons why it was very difficult to believe the phenomenon existed was actually because of the poor quality of various pictures. For example, here's a picture from Romania from the 70s. This is a courtesy of Seismological Society of America. What exactly is this showing us? It's showing us something, but it's hard to actually distinguish anything here. On the other hand, this picture by Jim Conacher taken in Alaska in the 70s shows us something with slightly more detail, unusual yellow lights above a lake. But in this case, it's still kind of difficult to explain what exactly we're looking at, or even if this is a real phenomenon. But both of these phenomena were followed by a relatively powerful earthquake. But the reports of these lights appearing after earthquakes actually have a very long history of being reported in a lot of different literature. As a matter of fact, the first ever mentioning of an earthquake light was back in 869 in regards to a relatively powerful earthquake in Japan. But more and more reports start to come out in the 20th century and way more in the 21st, especially with the advent of CCTV and various smartphones that do have much more powerful cameras. And in every single case, it would involve some kind of a relatively powerful earthquake, at least 5.5 on the Richter scale. And the interesting thing is that usually these lights were classified as either one of the two. Either unusual globular formations usually flying above the area where the earthquake would occur eventually. This is something that happened back in 1975 in Hawaii. Or the lights generally resembling a typical aurora, but usually white or blue in color, with the lights themselves appearing and disappearing in just a few seconds, occasionally lasting for a minute or so. And so, for example, in 1930s, once again in Japan, there were lights that were visible from a distance of about 110 kilometers. But more recently, the devastating 2008 Sichuan earthquake produced lights that were visible from approximately 400 kilometers away. None of this was recorded on camera, or at least not reported by media, but it was reported by several witnesses. Similar phenomena were seen in 2003 earthquake in Mexico, in 2007 earthquake in Peru, 2009 earthquake in Italy, 2010 earthquake in Chile, and even the powerful eruption of Sakurajima volcano also resulted in the production of these lights. Or at least that's what was claimed by the eyewitness accounts. And up until about 10 years ago, most of the scientific community was still relatively skeptical about the existence of this phenomenon simply because it seemed a little bit unrealistic. How exactly would a light be produced because of the earthquake? Yet more and more reports started to come out, and with the advent of social media and more importantly smartphones, we started to get actual evidence, video evidence. Now at first it was just photos, once again showing us unusual lights. For example, this is from 2009 in Italy, with certain pictures and videos not really showing much, and certain other pictures looking a little bit too unreal, even though these were actual photos. But then we started to get actual footage from actual witnesses using smartphones. And this is absolutely incredible. This shows you what these earthquake lights were like during an earthquake in 2021 in Acapulco, Mexico, with these phenomena being captured from a lot of different angles by a lot of different people. And some of them just being completely unreal. It literally looks like the entire sky is exploding with these lights. Now what exactly is happening here? And more importantly, is this an actual real scientific phenomenon? And of course not everyone believed what they were seeing. Well, some of the explanations for these lights do make sense. These were maybe exploding transformers. As a matter of fact, at least one video from Acapulco that you see right here, and as always you can find in the description below, shows us what happened right there. This transformer exploded, producing the lights above. But this single explosion doesn't actually produce enough light to illuminate the skies just as we see behind it. So something else, more powerful, was causing a lot of these other flashes. For example, in this case right here, the actual light seems to be coming from above the skies, not really from below where the transformers would be located. Similarly, in this video right here, it becomes obvious that some of the lights also seem to be different color, so they do seem to have slightly different origin. And so following this earthquake last year in 2021, that's sort of when a lot of scientists suddenly realized that maybe this is something after all. And specifically because even very recently, both in China and in Japan, we had even more evidence for the existence of these unusual earthquake lights. These lights you're about to see, that's from the very recent earthquake in the same region of Sendai in Japan, with this video being taken on March 16, 2022. And as you can see from the power of this flash, it's unlikely to be a transformer. Something way more powerful would have to produce the light we're observing. But that's where we enter the realm of unknown. At the moment, it's really unclear what produces this. But from all of the available evidence so far, some of the scientists established that it seems to be possibly two different phenomena. One of them, resembling a typical aurora, usually happens either during or slightly after a very powerful earthquake, at least 5 on the Richter scale. But then there is also something that seems to happen before the earthquakes, sometimes even a few weeks before the earthquake occurs. And this is something that's observed very close to the epicenter. And sometimes this resembles a ball of light, sometimes it resembles something slightly different, but it seems to resemble a typical object we would classify as a ball lightning, or sometimes resembles a ball of light that hovers and disappears slightly after. So yeah, it sure sounds like a typical UFO, but a lot of these events seem to be pretty much natural. But aliens, they're not, because there are actual scientific explanations for what could be possibly happening here. It's just not entirely clear which explanation is the best. For example, in one of the explanations, it involves a chemical reaction. In this case, through the breaking of different bonds inside certain minerals, for example dolomite or rhyolite, it's possible to produce very high stress that can then release oxygen that actually becomes ionized. And once these ions escape from the cracks in the rocks, they can then start ionizing the atmosphere, forming plasma that emits light. Actually, the plasma ball you see right here is produced in this way, with certain experiments in the lab suggesting that this could actually explain some of these phenomena. So for example, by having certain locations with relatively vertical folds or cracks, this in theory can produce a lot of ionized oxygen, thus producing a lot of light. But that's of course just one of the explanations. The other explanation involves the principle known as piezoelectricity, the same principle usually used in a typical quartz clock. And here, through the mechanical motion on the quartz crystals and through sheer power of the earthquake, this can actually produce a lot of electricity, which once again could maybe produce some sort of ionization in the air. Another explanation involves the magnetic field of our planet, and specifically the interaction between these very highly electrically charged rocks and the magnetic field above the region, with these regions then triggering some kind of an aurora-like event. And the last explanation involves a phenomenon that we know exists but also do not understand. This is known as the triboluminescence. It's the unusual production of light when certain minerals, in this case once again crystal, are mechanically pulled apart, ripped, scratched, crushed or rubbed, and end up producing the light that you see right here. And so trying to use this phenomenon that we barely understand to explain another phenomenon that we really don't understand is not really good science. But nevertheless, it is one of the possible explanations for how some of these lights that have been observed in various regions on the planet seem to be produced. But even though we don't understand what's happening here very well, we do understand where these events seem to occur. The vast majority, or about 97% of all of these lights, for the most part have been associated with these so-called subvertical faults. The regions which only cause about 5% of all of the earthquakes on the planet, and essentially represent a region where the tectonic plates are stretched and pulled apart, causing various vertical cracks. In contrast, the majority of earthquakes on the planet are usually caused by the subduction zones, where one plate is slipping below the other. And so knowing where these earthquake lights happen could one day help us figure out what's happening here. But more importantly, or more practically, it's already been suggested that detecting these lights can actually help us predict future powerful earthquakes. With several studies from Italy, for example, already suggesting that it has been done in the past, where people detecting the lights and knowing about this phenomenon has actually provided shelter for several other people in their basement, which saved their life. In other words, by being able to somehow detect these lights across the planet, possibly using some kind of a satellite system, at least in theory, we could maybe predict earthquakes, powerful ones, or at least in certain regions of the planet where these lights do appear. Which of course makes this a pretty interesting topic that we're going to be exploring again once more studies come out. But I guess until more discoveries, more evidence, or more explanations, we're going to have to leave it at that. It's still a pretty big mystery. It's still unknown whether this is a legit phenomenon or simply some kind of a correlation with something entirely different. And it's still unknown whether all of this has some kind of a more boring, mundane explanation, and it's obviously still unknown what mechanism produces any of this. But I guess once we learn more, or once the scientists understand this in more detail, I'll make sure to follow this up with another video. So make sure to subscribe, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Support the channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.
Alright. Okay. Alrighty, that was Anton Petrov, and Pretty interesting presentation. Okay. So it was interesting that he identified a certain kind of fault, the vertical fault, as being more implicated. Has anybody heard of that?
Friedemann, you'll need to unmute.
Correct. Thank you, Did. So he identified the vertical faults as the source of earthquake lights, and then said in the next sentence that the earthquakes themselves are more commonly associated with subduction zones. So there is some differentiation between the two phenomena that is certainly of interest in order to maybe understand more how they are generated.
Yeah, that got my interest for sure.
Yep.
There's been quite a bit of research by a man named Jorge Heraud in Peru. Heraud is his last name, and he has shown that it's connected with coseismic activity. That's activity that is occurring during an earthquake, and as the earthquake waves pass through. Friedemann, help me out with this denser rock. Is it igneous intrusions?
No, it is actually any igneous rock, but also every high degree metamorphic rocks, which constitute a major part of continental, the mass of continental rocks, are either intrusive granite type rocks or highly metamorphosed sedimentary rocks. And in both cases, the defects that I have been studied specifically become accumulated in these rocks, and they are the original source of these phenomena that lead to the emission of earthquake lights.
But right there around Lima, I guess it's the granitic intrusions. The harder rock is once discharges are traveling along, these dramatic eruptions of light occur there. Isn't that correct?
Yes, Peru, of course, is part of the huge subduction zone that goes all along the South American continent. And it is maybe even amplified by the fact that when you look at the map of Peru, Peru is sitting in the corner of that subduction zone, where the subduction zone changes direction from east to south, from diagonal to almost north-south vertical. And so, yes, this is part of this large subduction zone, and it seems to be particularly prominent in this part of Peru.
And could you say a little bit about why, as these charges are, as the seismic wave hits the granitic intrusion, what is it about that rock that causes the eruption to happen above?
Well, now you must give me 5 minutes to give the basic explanation. What I discovered way back when I started to study these phenomena was that we have to pay attention to the fact that oxygen, when you look at the periodic table, has two valencies. Oxygen mostly occurs at oxygen double minus. So most rocks, common rocks, are made out of oxide materials in which the oxygen has the valence, the oxidation state 2 minus. But in all rocks that are formed by igneous processes and by high temperature metamorphic processes, sedimentary rocks contain so-called peroxy defects in which the oxygen has changed its valency to 1 minus, and then two of these 1 minus oxygens are getting together and form a peroxy bond. And what my work seems to indicate is that when this peroxy bond breaks, we are observing an essentially electrification of the rocks. We are generating mobile electronic charge carriers, and we know exactly what these charge carriers are. They are electronic states associated with oxygen single minus. Normally, oxygen single minus seeks another single minus to form a peroxy, in which case it is kind of stable. But when we stress the rock and mechanically deform it, these peroxy bonds break and activate these oxygen single minus. And then a second process takes place, which is typical for or very crucial to understanding earthquake lights, that the otherwise insulating rock mass of the rock has now generated a bunch of highly mobile, positively charged electronic charge carriers, and they repel each other, and they thereby accumulate on the surface. And on the surface, they produce microscopic but very high electric fields, millions of volts per centimeter, which then exceed the ionization potential of air and cause a cascade of electronic processes that we recognize as a discharge. And they produce these lights phenomena in the atmosphere.
These, I think physicists call these charges that are liberated when the peroxy splits, positive holes.
Positive holes, right.
And that goes to something that was in the video where he suggests that maybe piezo or piezo, however you want to say it, is responsible, but we know it can't be. It can't be, because that is a momentary discharge. It's, you apply the pressure, the crystal responds with a charge.
Yes.
In this phenomenon that Friedemann identified, it can be continuous. There's a continuous flow of these positive holes through the rock. Now, we know that rock resists electricity tremendously. It's not passing through the conductance band at all. It's because, as he found, it's traveling through the valence band, that it can travel, these charges travel at electronic speed to the surface.
Yes.
Something on the order of 100 meters per second.
300, up to 300 meters
Up to
per
300.
second. Yes, and yes, these are essentially defect electrons, which have been given the name positive holes. A defect electron in semiconductor language is a hole. And then people becoming interested in the electric conductivity phenomena of oxide insulators realized that these hole states can form also in oxide materials, and then they gave it the name positive holes. I didn't give it, somebody else. I don't even remember who did it. So these positive hole charge carriers are holes or defect electrons that are associated with a valence band. So missing electrons in the valence band. We don't have to activate them up into the conduction band, which is way up, too high to be achieved by normal temperature phenomena. But they are mobile and they hop from oxygen to oxygen atom. We measure the speed of propagation. If you measure them in a linear system, you reach 200 to 300 meters per second. In a three-dimensional system, they start out at a speed of about 100 meters per second, slowing down as they propagate outward. And that is consistent with observations with which the charge carriers are propagating in nature when earthquake prepared situations arise.
And at L'Aquila in Italy, they observed earthquake lights. Some people sought shelter from one household where the father happened to step out at night and see these lights and think, I don't care what they're telling us about it being safe. I've heard that these lights occur around the time of earthquakes. He got his family out. They survived. There was devastation throughout the city.
That's correct. Yes.
It's the old masonry style Italian buildings.
Yes. There were, I don't remember exactly, but there was a relatively high percentage of people that were killed in the L'Aquila earthquake. Because L'Aquila earthquake happened almost essentially under the city, the town of L'Aquila.
So he mentioned that earthquakes could be predicted by this, but this is largely a co-seismic phenomenon. It's happening around the time of the earthquake. The critical thing here is that there are many other effects that happen from positive hole activation. Signs can be detected up to 2 weeks in advance of an earthquake. And in Peru, they have already detected. Last time I spoke with Jorge, he said they had pinned down some 80 plus earthquakes that they had accurately predicted.
Yes.
And I'm sure it's a lot more since then.
Yes.
Peru, they have constant earthquakes.
Yeah. Well, just to complement what you are saying, Alberto, is that earthquake lights are, of course, the visible light in the visible spectrum. But before earthquakes, when rocks are stressed, there is massive infrared emission, which is hardly ever recorded. And if it is recorded, it is misinterpreted as thermal anomalies. And you see when you go into the literature or on the web and look at thermal anomalies prior to earthquakes, there's a lot of information where people see evidence for so-called temperature increase prior to earthquakes. These are not temperature increase. This is increase in infrared emission from the surface of the rocks, which is not a temperature increase, but a physical phenomena that is driven by the movement and the recombination of positive hole charge carriers.
And this is where the classical physicists who work for the USGS tend to talk past the quantum physicists like Friedemann, who are saying, no, this is a surface emission. The positive holes rise to the surface, and then they cause an emission there because the ionization field is very tiny. It's right there at the surface,
yes,
where the oxygen meets the atmosphere meets the rock or the soil. And so what the USGS would tell you is, no, we never see a temperature rise, but they're putting thermocouples deep into the earth, and they're saying it's not there.
That's right. Yes.
But it's an IR emission. It's an infrared emission. It says it can be plainly seen in the Hector Mine earthquake, in the Bouge earthquake, in was it Iran, or a bomb earthquake, and
bomb earthquake in Iran? Yes.
Yes. And what was it, the Bouge earthquake in India?
Yeah, one of the best, of course, is the L'Aquila earthquake, because it so happened that in L'Aquila, excellent measurements were performed. Not expecting anything like this, they just observed these infrared emission by chance.
So Nevin Bryant is a name to look at if people are looking for that. He is a JPL researcher who looked at the Hector Mine and other earthquakes and saw, and we're talking about thousands of square miles may light up around a zone of activation, because while an earthquake, the hypocenter, the place where the rock finally breaks and splits, it might be a very small spot. There's this huge tension building up in this volume of rock all around it. And it's lighting up the earth.
Yes, and it is emitting in the thermal infrared window, and that does not mean that the surface becomes hot. It is a very sharp infrared emission in certain lines, you can put a thermometer or a thermocouple there, and you would probably see no temperature increase. Even though when you look with the infrared camera, it looks like the rock has become 10 degrees, 15 degrees hotter than before. So the phenomenon is huge compared to what you would normally expect on the basis of classical measurements of temperature with the thermocouple.
And Nevin was very careful in his research to point out that no, there's no heating from air moving downhill or anything like that in any of these instances. These are too large of an area to be heated that way, adiabatically, so quickly. And this is an effect that comes on like a flashlight. Boom, it's there. The Earth lights up. And then in the infrared, not like the earthquake lights, not visible, and that can last for a long time.
And could also precede earthquakes. And since nobody normally looks for these infrared emission, they have not been observed because people are not set up to look at this relatively difficult region of thermal infrared in about 10 to 14 micron range region.
There's a Russian by the name of A.A. Tronin. You'd find him under the literature that way, A.A. Tronin.
Tronin, yes.
Yes.
He was
and
one of the early reporters.
He was looking at U.S. Weather satellite imagery that is just by chance. We got lucky. The infrared bands that the satellites, the GOES satellites cover, also happen to be where that emission occurs.
Yes.
So we could have made this progress, 20 years ago if the officialdom had the ears to hear it.
Yes.
But there are so many other effects. I want to point out European Physical Journal. This is the January 2001 issue. If anybody wants to go looking for this, wow. You see all the myriad effects that are generated. This is edited in part by Friedemann, Didier Sornet of Switzerland, Guy Ouillon, Arnaud Mignon. And it's the global earthquake forecasting system towards using non-seismic precursors for the prediction of large earthquakes. I hope Anton will look for this because it would be a tremendous resource to him.
Yes, and please contact me if you want any of these or all of these papers in electronic format. I, as the editor of this, the guest editor of this issue of the journal, European Journal of Physics, I have, of course, electronic copies of all the papers published in this issue.
So it's volume 230, number 1.
Yeah, last year in January it came out. Mm-hmm.
An awesome piece of work.
Thank you.
It's just that there are so many different effects. And right now we're losing some of our pioneers, like Doug Reckenthaler, who passed 5 years ago, I think now already.
Yes, yes.
Doug came up with a way to image disturbances in the ionosphere just using GPS signals that are freely available from satellites continuously passing over.
Yeah, and we should mention that Doug, when he did this work, this was all funded by the DoD, because the military, of course, has interest in understanding what happens in the ionosphere.
And Doug had a patent on a prediction system based on imaging. He could show you a huge plume of activation over Fairbanks in the weeks before a quake.
Yes, yes. But the USGS just refused to look at the evidence and just badmouthed this whole work, and that's why it has stagnated. There's essentially no possibility of getting, at least not USGS support, And if you turn to the National Science Foundation and you said you would like to study earthquake lights, you get a letter from the National Science Foundation say, yeah, turn to the USGS, they are in charge of it.
So can we list off some of the effects, the pre-earthquake effects, like the ones that Jorge's measuring? He's measuring extremely low frequency transmissions, isn't he?
Emission, not
emissions, rather emission.
As we answer that, Marilyn had a question: how much time is there between sighting of lights and the earthquakes, and are they seen at all magnitudes? And it seems like earlier you were saying the lights happened during the earthquake, right?
The visible lights
visible.
tend to happen during the earthquake, but the infrared emission precedes the earthquake by as much as a few days, maybe even 2 or 3 weeks.
Wow. Days to weeks. Okay.
And the very low frequency and extremely low frequency emissions also start as much as 2 weeks early, and you can use them. The volume that's under pressure starts to send signals, and by averaging them with an algorithm, you can pinpoint pretty much within 40 miles where that quake is going to occur.
Yeah,
where the hypocenter is of the quake.
Yeah. Can I rephrase your
Yes, please do.
Please. So for those of you who would like to understand the mechanism, the process is the following. Every rock in the earth, both igneous rocks and high-grade metamorphic sedimentary rocks, contain what people call peroxy defects. Peroxy defects are pairs of oxygen where each oxygen has a valence of 1 minus compared to the common valence of double minus. And when the peroxy defect, which is very often a link between mineral grains. So when mineral grains are shifted by tectonic forces, these peroxy defects are broken in large numbers. They recombine as well, but at the same time, some of these electronic charge carriers are spreading out as a electronic charge cloud that travels at about 100 to 200 meters per second. And they can travel over distances of 100, if not hundreds of kilometers. When they arrive, when these charge carriers arrive at the surface of the Earth, they can recombine to form peroxy again. And this recombination is very energetic. The peroxy forms in a very highly vibrationally excited state, though this emits infrared emission in the thermal infrared band around between 9.4 and 14 microns. And that is what is the thermal infrared anomaly that we have been talking about. So this is a wonderful process, but the visible light only occurs when the number density, the number of these activated charge carriers is so high that you get a breakdown of the air through ionization of the air, and you get electric discharges, which then form a discharge light emission, the earthquake lights. So the earthquake lights are different from this infrared emission. The infrared emission comes directly from the rock solid surface. The earthquake lights comes from the discharge of the breakdown of the dielectric insulation of the air, and just like in a high voltage tower, you sometimes see electric discharges happening, and they are accompanied by glow discharges by visible light.
Ionization also has other effects. That an ion plume rises, and
the
it
ion,
can affect human beings. It affected me.
yes,
I
because
was sitting at my desk in Anchorage, next to a big metal post in the building,
yes,
and we were virtually at the epicenter of an earthquake there. So I was like prime target to receive a dose of positive ions. And in spite of the name positive, they don't make you feel good. They make you feel anxious and sickly and nauseous. I became so nauseous that at lunch, I went home and I was going down the stairs hand over hand on the rail like I was an 80-year-old guy, and I was then 40s. I mean, I was really quite affected by it. I went home, laid down, and after a couple hours, I was able to return to work.
yeah, this is the known effect of positive ions. It's actually, you probably all have heard, there was maybe 10 to 15, 20 years ago, a uproar about the sick building syndrome. There were office buildings in which the companies reported that their employees had an unusually high number of sick leave. And when they investigated this, I think this was in the early 70s, the architects determined that the buildings were made in such a way that positive air ions were easily formed at sharp corners in the building, and then the positive air ions affect the physiology of the people working and living in the buildings. So there were actually changes in the building code which have been instituted ever since, so that you avoid the formation of positive air ions. It is,
but we don't need to rely on individuals' anecdotal accounts like my own. There's been research in the Amazon with animals, in Italy with animals, in Russia with ambulance transports, where they showed that you were more likely to be transported before a quake for things related to anxiety and hyperventilating and whatnot, and after the quake for injuries, of course, but that both went up around the quake. It's just that they were different before the quake than after. Before the quake, people were feeling it. We think we don't sense the earthquake, but it affects us when it's coming, whether we realize it or not. Anxiety levels rise among those who are most susceptible.
well, I should mention, just to support what you are saying, I grew up in Central Europe, in Germany, and there we have thunderstorms, like you have it here in the middle of the country. And prior to thunderstorms, you often, before the rain starts to fall, there is this very uneasy feeling. You feel a kind of heavy feeling. And the reason for this is that the thunderstorm cloud, the underbelly of the thunderstorm cloud, has a very high distinct negative charge. And it accumulates positive charge underneath in the surface of the earth as a mirror image of the charge in the cloud. And as the cloud is drifting, that charge cloud in the ground is also drifting. And people are affected by this positive charge. And this is the same charge that is being activated by earthquakes in larger concentration and larger number of charge carriers. So it is an earthquake is an amplification of this pre-thunderstorm phenomenon that those of us who lived in areas where thunderstorms happen may have experienced, that you have this kind of heavy feeling uneasy feeling because of people don't know. I myself never knew when I grew up that there was a physical or a scientific explanation, but I think it has to do with these positive hole charge, which are highly oxidizing, and therefore through their oxidation capabilities, they seem to affect our physiology.
And as I mentioned, Rachel Grant is a name that people might want to look for if they're interested in human or animal effects.
Yeah, she's a biologist in England.
John, or Alberto, I mean, you said you had a list of effects. Was that the list you were just talking about?
I could just, you can relate to positive hole activation, fluorescence in water chemistry changes. In Turkey, they can see that before, the government requires, as it does here, anybody who's selling mineral water to keep constant records. And they go back decades for the whole operation of the plant, of their water quality, to say it's so great, okay? But then sometime before an earthquake, it changes because you're having these positive hole currents going through the earth. This is not a typical electron current. Electrons wouldn't go through the rock. It's this positive hole current flowing through. It changes the chemistry because it creates peroxide wherever it encounters water.
Yeah, it forms hydrogen peroxide in the water. And that is why the water chemistry is changing, because it also dissolves the minerals faster.
So in dissolving the minerals, it brings in other metals that you don't want. So they have to throw out that batch. So the plants know all about this.
Yes, and you are right, Alberto, because Turkey, with its very active seismic history, has a long history in their water analysis data to show that prior to earthquakes, there are changes in the water chemistry.
So we've talked about cloud formation a little bit, how it's influenced, also lightning statistics. Once you wrap your head around what Friedeman's discovered, it changes the way you look at everything. I was walking around AGU and I saw a lightning distribution map of the world, and you see that lightning is happening over continental masses. It doesn't happen far out to sea because any positive holes reaching the surface there would be hitting the bottom of the ocean, and they'd be instantly converted into peroxide.
Into hydrogen peroxide, yes.
But what I noticed was trailing off the continents, windward off the continents with the Coriolis force, you can see that there is a plume going out to sea from that continent. And it's never on the side that the prevailing wind is hitting the continent.
Against the wind, yes.
It's always away from the continent. And in fact, you know, when I grew up, they told you that that lightning had something to do with moisture going up into the air and carrying ions, and that's why you felt humidity, and that was all bunk. That's all wrong. The Arabian Sea is just as black as night in the lightning photo, but except at the south end of India, there's a little plume coming off, because that's where the Coriolis force changes. And when I saw that map, it was like an overlay of a Coriolis map.
An aha moment, right?
Yeah. So I rushed over to Friedemann, and then I started grabbing other people. But so you would never see that if you didn't know what you were. You know, if you didn't have Friedman's theory, you can't really see the world as it is. The world is a quantum world. It's not a classical world. It's not like quantum is just something we find in tiny things. It affects everything. You know, like you see red, you're seeing red because of a quantum effect. So it's not just quantum is everything. It affects everything. And this positive hole theory, we have to get solid state chemists involved in this. The flip side of Friedman's theory is that as during crystallization, certain ions get thrust out. They don't get included, and they end up everything is being highly reduced. So you get highly reduced species. Am I correct here, Friedemann? Carbon, nitrogen, and very basically the elements of life come together and start forming compounds. Now in space, we found every amino acid, well, not every amino acid, but the nucleic acids of DNA and RNA. And Friedemann and Mino, his son, who's unfortunately gone now, but discovered that there was a way that this positive hole theory could explain why it is that during crystallization, these elements in a highly reduced form, meaning rejected from the crystallization dance, but very ready to combine with anybody that comes along, are segregated into little, what do you call them?
Dislocations.
Dislocations within the crystal,
right.
Little gaps.
Yeah.
And in there, you find all kinds of interesting things. One thing that Friedemann and Mino focused on was the lipids that form the cell wall. The two lipids in particular that they found, if you just take these lipids and put them in water and whip up the water, you get what look like cell membranes forming.
Yes.
But there are many other things forming in outer space. It's everywhere. It's like we're in a turnkey universe. Life is just waiting to happen.
Yeah, but you are probably, Alberto, you are going very quickly through think of a big book, and the first 100 pages are about the earthquake, and then the last 100 pages about the effect of life.
So we're getting a little bit off of
you're
life,
getting carried away. Yes.
I just
but they are linked. You are right. They are linked.
But abiogenesis is why we're talking about earthquake lights. We wouldn't be here if there wasn't some way to get from rock to life. And this theory, positive hole theory that Friedemann Freund created, and I call it Freundian physics, explains all of those things.
Well, you're too generous. So, yeah.
I've got a question. So, are the geological societies of other countries as stuck in their ways as the USGS, or are they taking advantage of this new knowledge, or how's that playing out?
Well, one thing is that in the science field, of course, the US are reigning supreme. So if some mainstream theory or science is promoted, for instance, by the USGS, just the power of the USGS is prevailing on most of the other equivalent geological surveys in other countries. Also, of course, there is a lot of geologists from other countries get their training at the USGS here in Western Virginia or here in California. So I understand your question, David. It is a mixture of science and politics, and of course, science is never completely free of politics. So if the USGS is adamantly opposed to accept a theory that would explain a natural phenomenon, they have shown in history, even though the USGS as an organization didn't exist, but the Alfred Wegener suggestions from the formation of organic molecules in rocks and the origin of life were kind of put away, declared to be unacceptable for almost 50 years. And the same with the continental drift. Wegener proposed and demonstrated with excellent observational data that the continents are moving and have been moving for a long period of time, but the people at that time just rejected these observations and stuck to the, at that time, prevailing idea that continents are not moving.
In fact, a lot of these ideas have been around for a long time before they're even recognized, and with having to do with animal effects and how the USGS treats somebody who is going off the reservation. I'd like John Derr to remind us about a woman named Ruth Simons and what happened. John, are you with us? Oh, I guess he's falling asleep. Anyway, John, Ruth Simons, do you remember her?
Yes, of course I remember Ruth Simons.
Could you tell us what happens to somebody who, unlike Rachel, wasn't working in an electronic era of transmitting things by computer, and who didn't have the benefit of the cameras that we have today that will sit around and watch the animals for you, and who did the hard work of going to the Amazon and did research on animals? Tell us what happened to Ruth, because she deserves to be remembered. You have to unmute, John.
Ruth Simon is known by many high-level scientists in earth science. She's the one who taught them all how to read seismograms at Columbia University primarily. She was interested in animal behavior. She had a cage with some big South American cockroaches and an upside down phonograph cartridge with a big disc attached to it where the needle would normally be, so that any critter moving around in the cage would brush against it and cause a tick in the electronics. She had some good data from an observatory in Southern California that mysteriously disappeared between the Denver Federal Center and our office in Golden. We never knew ultimately what happened to it, but it was logged in the mail system at the central receiving office in the Denver Federal Center, and then never made it to her desk in Golden.
And this was probably, you presume it was tossed by somebody.
Yes, she had, her work was very unpopular.
And could you tell us something you overheard Waverly person say about? I understand somebody called USGS Boulder asking about whether there was anybody there who was doing research on animal research, on animal effects pre-earthquake.
Yes, that did indeed happen, and Waverly denied it. We were in a common area with very short partitions, and a number of us heard Waverly's end of the phone conversation.
And my understanding is that what you heard him say was, "I'm sorry, there's no such person here doing animal research."
I've forgotten the exact words that I gave you, but that is in.
I didn't get them from you, John.
Oh, you didn't? Oh. Well, I was just I was there and heard it, and there were all sorts of repercussions.
Interesting.
Yeah.
Because
So this is a kind of behavior that me coming from outside the sciences, I've got an English degree from Duke, an MA. It led me to conclude that science isn't so much like what they taught me in high school as like high school itself. And it shouldn't surprise anybody in the audience hearing that, because politics is everywhere. Human relations is everywhere. And power politics matters most when there's money on the line. And we've got $1 billion agency carrying a big stick all around the world. And Jorge Heraud has to be very quiet about his 81 earthquakes that he's pinpointed.
Yes.
Even his government relies on him. A few years ago, there was a meeting of Asian nations
Trans-Pacific meeting, yes.
Trans-Pacific meeting in Peru. And Jorge said, "What am I going to do with this information? I'm not allowed to distribute it publicly, but it looks like there's going to be an earthquake when we're going to have all these heads of state and important people here." And so it was transmitted to the president of Peru. During that conference, there was an earthquake. And he had called it. It was going to be a 4. It wasn't a very bad one, but he had called it. And the president leaned forward and reassured the assembled heads. He said, "No worries. We brought you today for today's meeting to this building because one of my colleagues from school told us there would be an earthquake. And so you're in a perfectly earthquake resistant building. And he did not predict this to be a large earthquake anyway."
Wow.
So if the president of Peru is counting on it, you know that it's reliable.
Right, that's a great story. I had not heard that one.
Yeah,
That's interesting, yes.
that happened.
Yeah.
And so in spite of this wonderful system of detecting the early, magnetic vibrations that we say are ELF or VLF emissions, and that he can pinpoint, you still haven't heard the name of Jorge Heraud in New York Times.
Right.
And you likely won't for some time to come. When I wrote for the New York Times, they actually killed my story. First, they asked for 2 sidebars. Then after I turned in the sidebars, they said, "Well, we've decided this is too positive." And I thought, well, do you want the facts or do you want a he said, she said?
Yeah.
But I knew that in the meantime, they had probably talked to somebody at the USGS and they told them earthquakes can't be predicted. I've got another book here. It's, where is it? It's a shameful disgrace of a book, Predicting the Unpredictable. It's by USGS spokesperson, Susan Hoff.
Right.
How in the world are you ever going to predict something if from the get-go you've decided it can't be predicted? And it's because she's stuck in classical physics, and classical physics can't tell you, how far I have to bend this, when the pen will break as I put on the pressure. Nobody can tell you that. It will be a chaotic process at the last minute. But what Friedemann can tell you is that the pressure on the rock down below, that is rising exponentially long before the break occurs.
Right.
And that's what starts the transmission 2 weeks ahead of the quake. Imagine that, 2 weeks. And we can't get this news out. That's the effect of the biggest gorilla in the room. That's what politics is about. They get $1 billion every year, and they have taken research money and turned it into operations money, because the only way you can get a grant is by doing research using their Seismo network. Very often it's all related to using their stuff. And until we get out of this idea that you can only forecast quakes by classical physics, we're never going to forecast them. In that case, Susan Hoff is right. She will never predict a single earthquake. But in here, Friedemann has, you can go to researchgate.com and put in Friedemann and see how many peer-reviewed published papers this man has managed to amass, in spite of the fact that he's continually being trashed. In here, she says, Friedemann, she misrepresents his work, and she says, he may not be completely out to lunch. Well, thank you, Susan.
Damning with faint praise.
Yeah, well, getting back to your original question to me in this series, what I heard over the partitions was Waverly lying to a major publication outlet in a way that was just demonstrably wrong, and I could see that it could indeed create problems for the USGS. Back in those days, we had human networks for notifying people in the event of earthquakes, and one aspect of it was that those of us who were on call had the home phone numbers of USGS public relations people, and we were to call them, and did indeed, in the middle of the night. I mean, there were 3 a.m. phone calls on a number of occasions, and I was part of this network, and had indeed telephoned the head of public relations in the USGS at 3 a.m. with these notifications. So we had a certain rapport, as you can imagine, in that situation. And what I heard was, it seemed to me as if it was going to cause us all sorts of problems. And so I called him, not at 3 a.m., but in the daytime, just to give him a heads up as to a kind of problem that we were liable for. What I didn't realize was that his office was directly across the corridor from the head of the USGS, and they were best friends. And they got together shortly thereafter, and the word went to the head of the USGS. And what happened was not exactly a popular event, and I ended up in the middle of it.
I'm sorry, I'm not following what you said to him exactly.
Oh, I told him that Waverly had lied egregiously to it. In this case, it was somebody, I think it was from the National Geographic Society, about animal behavior research that was supposedly not, Waverly denied that it was being done.
glad some of these details are getting filled in.
Yeah, right, right. And it, anyway, that's how it happened. And I was then in trouble with the local management for having become an inadvertent whistleblower. Just just to give them a heads up that they were likely to have some problems.
Yeah, yeah. Similar things have happened to Friedemann. Similar things have happened to just about everybody in this field.
Yeah.
You know, Masashi Hayakawa in Japan, he works at a technical institute, but he actually discovered ionospheric, pre-earthquake ionospheric disturbances, which later Doug Reckenthaler was able to come up with this nifty system for imaging.
Mm-hmm.
Masashi did it the hard way. He was using very long baseline radio between points. He should have been at the University of Tokyo years ago, but now he's probably heading into retirement, having never moved beyond the technical university.
Mm-hmm.
And it's because a USGS person or intellectual ally moved to Japan, and Friedemann, what's his name? Anyway, yes. I'm not catching it. You're not mute. You're on mute. Unmute. David, can you unmute him?
Let's see. I can ask.
His name is Geller.
Pardon?
Yeah.
His name is Geller.
Oh, yes. Robert Geller.
Robert
And I've talked
Geller.
to him, and he's
Yes.
absolutely convinced you cannot predict earthquakes. You know, it's the same dogma. You cannot predict it because they've decided beforehand that there won't be any other way. If anybody comes with some non-classical way to predict, it will be off the table. So he trashed Masashi Hayakawa's work. And basically in Japan is where seismic science really got underway. A British scientist went there and basically invented it. And I don't know I don't recall his name just off the top of my head. Guess I'm getting old. But he was looking from the very beginning, not just at seismicity, but magnetism and electrical discharges and everything. Because in Japan, you can't miss earthquake lights. It's like Peru. It's a seismic hotspot. So they had known for centuries about these things. It wasn't until the 1960s that the USGS got around to admitting, oh yeah, that sometimes happens. We don't want to talk about it. We can't explain it.
Yeah.
You know?
Now
This is what we're dealing with.
This brings up a question that I would be very interested in getting your feedback. It's one way of being sad and upset about the impossibility to bring out certain valid information, and then just use the capabilities of today's publication world to publish things. I have been able to publish a number of papers in international renowned journals, which I selected to be a little bit like a physical journal, because when you talk to physicists, they are not contaminated by this anti-feeling that is remnant in USGS circles. So the question is, what can we do together, the four of us?
Well, you raised a very important question, a very difficult question. I always thought that my big brothers would come in after me. You know, after that, when I got your paper, you sent me, this was one of your early papers, very early papers on thermal activation. And it was pretty dense, but I didn't have anything to do because I was far from home. So I just sat up late at night reading through it. And it all was very logical. And you showed the positive pole activation. And I believe this paper was from the 80s. And you showed it moving through a ceramic sample.
Right.
Or perhaps it was, I don't recall exactly what the sample was, but I was so excited when I read that I had to call you back. And within 3 days, we had a story in the paper.
Right. Yes.
And
I
was
kind of
really-
remember. Yes. Yes.
I was really eager to get the next story, but I assumed that the New York Times or the Wall Street Journal or some biggie Washington Post would jump on it and report on it. And it never comes
Never
because officialdom stomps on it.
Right.
And so I got the next big story. I got in on the cover of New Scientist. A story on one of the biggest, then the largest circulating science journal in the world. But again, nobody follows it. And to me, that's the mystery. Because when I first started asking Alaskan geologists, not one of them wanted to talk to me. I get referred to Switzerland. Switzerland refers me to Friedemann. They're afraid. People are afraid. And you have one brave guy here in this electronic room, and that's John Derr. And he never backed down. And he got an idea when he was a young man that there could be a way of activating electric charges in the earth. It wasn't Friedman's idea, but at least he was trying for an idea. And he stuck to his guns on this electronic phenomena, and he never backed down until finally, just around the time I think you were getting ready to retire, he gets a call or somebody, an email. Somebody asks him if he wants to write an earthquake lights bit for the USGS website. They're going to finally admit that it exists because the public is demanding it, but they're not going to send out a press release on that one. It's just, John, could you quietly write something for us and put it on the page? And that's the first time they admitted that they
Yes.
they wanted to talk about it.
I should mention, of course, that in my case, I don't want to kind of pat myself too much on my chest, but my work essentially started from the atomic scale. I was studying reactions in the solid state that are linked to oxygen, and oxygen changing its valence from 2- to 1-. And that's how everything started. And that's much later that I became aware that these phenomena have ramification in the area of recognizing earthquake phenomena, pre-earthquake phenomena. But that's much, much later. So many people out in the field, including those in the published literature, come from the opposite side. They come from the observation, which is sometimes very complex. And how do you extract from there the physics is very difficult. If you start from the basic process where you understand the physics and see, can you apply this to these observations? Then, yes, it works. So I'm a very lucky guy. And I should also, of course, mention here, because it's the first time I have the opportunity to doing so, that I'm a big admirer of John Derr's work, because I read it all way, way back long ago when I was trying to understand the complexity of these systems.
You told me that you had an aha moment as you were very busy thinking about your students' work. You were a young professor and you're walking through a park on their way to school. And your mind drifted to this wild-eyed idea from California about these earthquake lights that you'd heard reports. And suddenly it came to you, wait a minute, I've got the battery for this.
Yes, that was way back in Cologne when 45 years ago, when I often walked from home to the laboratory. That was an hour walk. But Cologne has beautiful parks, and about 90% of this walk was through the public parks. So it gave me time to think and to enjoy and to listen to the birds. And during one of these walks, I had an aha moment, because I have been reading about earthquake-related phenomena, which was for me some very exotic process that I never had heard before. Oh yes, thanks for reminding me.
Yeah, Friedemann, you've been very, very generous, and I would like to return a compliment and say that what you are doing is just absolutely revolutionary, innovative.
Yeah, I would like to view it this way, John. So let me repeat this idea. Could we do something together, the four of us, together maybe with others, and try to put together some 1 or 2 or 3 papers in which some of these ideas are presented with the solid state explanation as a background. Rather than building from the observation, trying to understand what is below, build from the mechanism and build up to the observations.
I'd love to. I know when I say that Friedmann's theory will change the way you look at the world, you don't need to be a solid state scientist. He is the solid state scientist. But once you get him, your world changes. I was walking through an AGU and I saw something about thermal vents. I thought, Friedemann says positive holes are activated by heat, by pressure, by shock. A thermal vent should have lots of peroxide forming. So I rush over to Friedemann, and he's a very careful thinker. He says, Alberto, you're getting ahead of yourself, because you have to realize there's a lot of sulfides at a sulfur vent, and they're much more hungry for electrons than oxygen is. So it will destroy any peroxide. But at the next year's AGU, we found, Friedemann and I noticed that there was a discovery made that not right there at the vent where all the sulfides are high, but near the vent, there was anomalous levels of peroxide, and nobody could figure out, why should this happen? Right. Well, Friedemann knows why.
Yeah. Yes.
Yeah.
And so just, it's a lively universe when you start thinking about Freudian physics. You know, it's just, everything changes. And I've wondered why his big brothers didn't come along, because while he's getting beat up by seismologists who were trained classically, all the solid state chemists and the solid solution chemists and solid state physicists, what are they doing? They're making megabucks. Why doesn't one of them come along and do the experiments? Because his basic experiment is so classically simple.
Very simple, yes.
You take a rock slab, you put in a hydraulic press, you let it sit overnight until it 24 hours, give it a long time to calm down from your handling of it. You have some copper tape on the end that you can get at any electric guitar shop. And then you put a wire from the press to that copper, and in between it, you put an ammeter.
Ammeter, yes.
Yeah, and then you squeeze, and you can see it instantly. You can see the rock battery turn on, and you know that the charge is positive, because the meter, instead of going that way, it's going that way.
Yes.
It's not a positive current. I mean, it's a positive current. It's not the negative current that you'd have with electrons. It's a
Right.
beautiful, simple experiment. Any high school student could replicate this experiment. Why hasn't a single solid state physicist or solid solution chemist come out of their, ivory tower and helped their little brother here? I don't know why it doesn't happen, but politics must enter in.
Yes. You mentioned getting together and publishing something. We put our toes in that water when I was invited to write an article for the European publication Encyclopedia of Solid Earth Geophysics.
Oh, yes.
Put
Yes.
out by Springer, and we did come together with a 4-author paper with me as the lead, as I was invited to do. The USGS has this publication process where everything needs to be submitted to that process, and when we got it together, I did that, and I was rejected by my branch chief, now called team leader, who consulted with naysayers in the group in Golden, which was over us. She in her position rejected the paper, and I said that I had been invited to contribute this, and I didn't think it was going to look very good for the USGS not to fulfill what was expected of us. So I ended up submitting it without USGS approval.
Oh,
Right. Yeah.
Oh, man.
I was a civil servant for some 20 years back in Germany, and Germans, when they do some bureaucracy, they know how to do it well.
Uh-huh.
So that's why when I came to America, I never wanted to become again a civil servant, even though I did have the opportunity to do it through NASA. I did not pursue this because it's restrictive. It produces, like you now said, you cannot publish freely. You have to ask permission, and if they don't give you the permission, that's it.
Right.
John even was had I think already bought the airline ticket and sought permission to use his vacation time to come to the AGU and meet with Friedemann, and I was going to report on both of them, and he was not allowed to come. They said, no, not even on your vacation time can you do this, because you'll be seen as a USGS spokesperson.
Yes.
That's how.
All right.
Incredible.
So what can we do?
What can we do?
I've got an idea.
right.
I do some articles for the Skeptical Inquirer that's published by the Committee for Skeptical Inquiry. And I think maybe the 4 of us could write an article for them, basically along the lines of, science does have the method to predict where earthquakes are going to happen in advance, and here's why you're not hearing about it. I think that'd be a fascinating article, and I'd be delighted to. They allow co-authors, so I think and the 4 of us could, send a manuscript around Basically, skeptical inquirer, you'll want maybe a 5,000, 7,000 word article with some graphics. So it'll have to be fairly concise, but you can say a lot in 7,000 words.
Yes, 7,000 words. I'm taking notes here.
Oh, okay. So somebody needs to start with a draft, or we could just circulate an outline first, and what should
I
go
think an
into it.
outline would be a great idea.
And once we had that outline, we could start writing to it, maybe individually, and then combine it as we go. I think that'd be a great idea.
Because really, this is though it takes a quantum physicist to explain it. It takes $50 to do this experiment, if that.
Maybe we should try to do that experiment as part of this article.
And
I'm a big
why didn't we? Why weren't these two guys allowed to come together? Because boy, the fusion of that would have been tremendous explosion of energy that we're only beginning to see. I'd like to see it before they're both gone. I'd like to see it before I'm gone.
Hello, John.
Here, Alberto.
Now we have a challenge in front of us.
Yeah. Well, does the audience have any questions? We've kept them very late, and I've probably bored them to death. I always talk too much.
Tish had a question. She asked, it sounds like this phenomena is only in certain types of rocks or certain types of earthquakes. What is the ballpark estimate of the number of types of quakes that do versus do not have the right type of rock or fault to produce the effect?
It's virtually all rock. Even sedimentary rock has igneous little bits ground up in it. So it's any rock that has an oxide. Don't need to worry about that. And you won't get any false negatives. They're all detectable. I'm going to be bold and say that they're all detectable. You might get some false positives. And here's why. Because sometimes when the earth slips, it will do it so smoothly, moving along like Fred Astaire or something. And you'll be up in the Puget Sound and you'll go out in your yard and you'll see that there's like a foot of change. And if that had happened here, it would have leveled buildings. But it's just so well lubricated that now that you won't detect. You'll have shown that pressure was building that caused it, but you will have made the prediction, but other people, human beings, won't detect it until after the fact. They won't realize that it happened. If they don't see a crack in their yard, they won't even think an earthquake occurred. So you get false positive, but probably no false negatives.
Well, it all boils down on this balance between the stress activation of these electronic charge carriers that we call positive holes, their tendency to recombine, and they constantly recombine as they are being stressed, and the flow. That's what causes the electromagnetic emission, the directional flow of these charge carriers, which causes then an electromagnetic signal. And so it is essentially a flow of electric charges down a stress gradient. And this is so simple to explain and to demonstrate in an experiment that you create a stress gradient, and you can take, to come back to John's question, what type of rock? Almost every rock. I did experiments with very pure Carrara level Italian marble.
Oh yeah.
And I squeezed it and I didn't see anything. So
it has no oxides.
Yes, because the carbonate structure does not allow the formation of peroxide. It's crystallography.
Peroxies.
Yes, the peroxies. But in the moment you get any other sedimentary rock or igneous rock or basalt type or peridotite, so slowly cooled from upper mantle temperatures, all these rocks are loaded with peroxy defects. And people have not, and we don't know, I don't know how to quantify these peroxy. So this would be a challenge to discuss among us, is can we come up with some idea how to measure the concentration of peroxides?
You mean of peroxy in rock, or?
Yes, how do we measure? We don't even know how much of it, how many of them are there. We don't know it.
You can't work backwards from the amount of energy that's released from the squeezing?
No, I don't
No.
think so. I don't think so. You work back, but then you cannot trust the numbers.
Yeah. Well, there's trillions of atoms in there, right? In the sample.
Of course, right.
Yeah.
If you could take a very small sample and then put that into an atomic mass spectrometer and see how the components divvy up, and then do a statistical analysis.
Is there a way of getting a peroxy in a gas sample and hitting it with a laser?
No, that's not.
Yeah.
What you would see cannot be transferred to the solid sample. Yeah. No, what I'm thinking, John, is one thing is peroxy is diamagnetic, but in the moment it breaks apart, it becomes paramagnetic. So you would see the moment you break it apart, you see a magnetic signal, and I have measured them. I have also measured the lifetime of peroxy, and most of them, 95% of them, recombine within 5 to 10 milliseconds. So unless you come up with measurements that would allow you to measure the paramagnetic property or magnetic properties very fast during rapid deformation, then you cannot, I think, determine the total amount of peroxy per rock.
Well, it's a tricky problem.
There are a number of very interesting phenomena that we could look at.
I for one, think I'm going to talk to our physics department. I'm friends with some of the people over there, and see if I can talk them into helping me do this $50 experiment. Sounds like that would be a neat thing to have, and maybe that would be fuel for a regular paper in a peer-reviewed journal, not just the good old Skeptical Inquirer.
Your rock can be a tile that you pick up at Home Depot.
Oh yes, easily.
Excellent.
Yeah, and it's already squared off and nicely, lightweight.
Okay. Yeah. Well, we have a whole bunch of those from our last project, so I don't have
Remember,
to
it needs to be quiet for a period before you apply the pressure.
Okay.
Yeah, I measured the lifetime of the.
I'll send you a diagram to get your input before we
please do so. Please do so, David.
Okay. Well, this has been just a super fascinating discussion. I'm delighted that all of you were able to participate, and I don't think we've heard the last of Earthquake Lights.
Okay.
So we'll post this on the YouTube in a few days probably. And that could spark some conversations right there, and I'll send it to Anton, who may express some interest and maybe follow up some more. He's got 500,000 viewers. So that was one of my question. Is this finally breaking? Now that there are more and more reports of earthquake lights, do you think there's any chance that the USGS might be inclined to actually look at what's happening?
Well, yes, over time, like the community denied for 50 years that there is continental drift. Eventually, then it became plate tectonics that became a big business.
Yeah.
And so the same would be true for peroxy. Once we have a breakthrough, we overcome the barrier and we lead to a broader acceptance, I would think, and I believe that John is would agree, that once we have solid proof of this, it would definitely be of it's undeniable.
Yeah.
And major interest.
With Wagner, he was dead 30 years, but with J. Harlan Bretz, who said that geology could change virtually overnight with the cataclysmic effects. And
Right.
he talked about the Missoulian floods that reshaped the entire Northwest.
Badlands, yeah.
Yeah.
He's one of my
I grew
heroes.
up in that territory. And he finally got recognized in his late 80s in Portland, Oregon, when the the big heads from back east finally came out and gave him a medal. And he said, "If I have any satisfaction, it's that I have outlived my enemies." And Freeman, hang in there.
Hang in there. I will.
There's still a few people that need to drop dead.
Yes. Yeah.
Okay. Well, it's been fun.
And we also see Gary Aldrich shows the camera is turned on now. We see your picture.
No.
Well, I'm a solid state, or was a solid state physicist, but not much in complex rock chemistry as you need. I was wondering if there's anybody, do you know of any sympathetic souls in AGU as opposed to the Geological Society?
Well, I kind of have withdrawn a little bit from these circles, and so I don't keep much of a personal connection with many people. I haven't attended the last 2 or 3 or 4 AGU fall meetings, even though we live just 50 kilometers away from San Francisco. So
Jerry, I think this would actually be right up your alley. Don't shortchange your skills.
No.
How about a paper for Jerry Friedemann? Could you send him something like rocks that snap, crackle, and whatever it was?
Of course, I can send to all of you, even if you already have it. It doesn't matter. I can send some reprints on some.
Yeah, if you send them to me, I can send them along to Jerry, and
yeah,
be interested.
Dave can put them up. Are they open
I can post them on
access?
our website if copyright concerns permit.
Yeah. Are the papers you had in mind open access or free access?
I would have to ask. I never ask actually, because I only distributed until now among colleagues, where of course.
Right.
We can do that
the
for
freedom
now, and
of
then
doing it.
pursue, posting it more publicly.
Yeah.
But do you
now,
have one classic Friedman paper that you could send to Jerry specifically that would talk about how all these effects, these diverse effects, have a solid state origin?
I really don't want to get very deeply involved or even try to get deeply involved. I had some medical problems that kind of stand in the way of that.
Yeah. I just thought you might find that interesting. That it's
I might find it interesting, and
Dave is going to do the experiment anyway. So
yeah, no, that needs to be done.
Sounds like a fun one. Well, it's almost 9 o'clock. It's been super interesting. Thanks, everybody, for hanging in there. And
Thank you.
So
Oh my
I'll
God,
let you
it
know
must
when
be,
this comes
what
up.
is it, midnight where you are, John?
Um, almost 11.
Oh
Oh,
gosh,
boy.
I'm Eastern time zone.
thank you
Oh,
so
just,
much. Sleep tight.
Couple more things in July. We don't have an NMSR meeting. We're taking our summer vacation, and somebody mentioned that earthquake in Elikila, and I think that was the same one, the 2009 deadly earthquake, and there were 7 Italian scientists who were charged and almost put in jail for failing to predict that earthquake.
Well, it wasn't really for failing to predict. What they did was they did predict. At least one of them said, I would sleep quietly in my bed. He made a prediction in a sense from the public's point of view that there was no danger, even though people were seeing lights.
Uh-huh.
Even though people were, their folk wisdom told them something was coming. And the scientist said, no, if it's me, I sleep quietly in my bed. And I would if I had a steel cage over me.
Great. So I think they were acquitted.
They were ultimately,
Yeah.
yes, acquitted.
They were acquitted, yes. Yes.
They- yeah.
All righty. Well, fascinating topic.
Yeah.
Thanks so much to everybody for participating, and
Thanks for organizing. Thanks for asking
you.
me to join.
all righty.
Yeah.
Well,
Dave-
we'll speak
Dave,
more.
before I sign off, knowing your association with the IRIS program,
Uh-huh.
I would be remiss if I did not mention that IRIS is absolutely in bed with the USGS. So.
So I'm in that
we're
regard,
gonna-
I'm actually retiring this month, end of June.
Ah,
So and I think I'm going to do this experiment with the physics department.
oh, congratulations.
I mean, it sounds like a physics.
It sounds like
experiment.
you're safe then.
Yes,
But
yes.
yeah, so I don't have to worry about my career at Pascal.
Good.
But could get some people excited over there. We'll see.
One thing I'd love to know if anybody at the Trinity test site had electronic measurements on the ground as the huge positive activation of the biggest bang that the world had ever seen. Sweat, they
Right.
would have seen that in the rock.
Wow.
Damn.
Yeah.
Well, the
I'd love to know
geologists seismologists are too much into mechanical physics. They don't understand.
No, but physicists were
semiconductor
looking at
aspects.
everything, I think,
Right,
possibly,
yes.
or should have.
Yeah, the Trinity side is actually an infield river channel. It's where the Rio Grande used to run, long time ago. So, I mean, you can get some seismic effects, but there's not any hard rock close. There is some hard rock over to the east
Uh-huh.
in the mountains that line the western edge of the. I'm having a senior moment. The name of that basin that the White Sands are in, Tularosa Basin.
Oh, yeah. Okay. Yes.
Yeah, but
The White Sands.
I mean it's several miles from those mountains. So
Well, I've heard that our government did some other tests later, so maybe.
well, yeah, I'm sure they did.
At some point in Nevada,
They did a lot of tests in Nevada.
Yes. Yeah.
Yeah.
Well, as you drive up to the Trinity site, if the light's right, you can see the burn radius quite clearly.
Wow.
Uh-huh.
I've never been.
Oh, all righty. Well, this has been
Yeah.
fascinating. Thanks so much.
Thank you so much, Dave.
And,
Yes.
No,
Thank you, John. Thank you, Friedman.
Thank
Thanks,
you.
everybody.
Thank you.
Yeah.
Thank you,
Thank you all.
Alberto. Thank you,
Yes.
Friedman.
Okay.
Thank you. Nice seeing you on the video. Thank
All
you.
righty.
Yeah.
Super interesting. And I think
All
we'll
right.
do more. Okay.
Okay.
Take care,
Bye.
everybody. Live
Bye-bye.
well, prosper.